Looking at the code from the previous Morsel, it may seem complex, but you will soon become experts at churning out these critical sections. To make things more simple, let's generalize the structure of each of the code blocks corresponding to the entry points and the exit points in the real critical section code that the readers and writers are performing. So these code segments here correspond to the enter critical section and the exit critical section codes when we consider read data as the operation that's the real critical section, given that what we really wanted to protect was the file. So this is what we want to control. And then we structure these code blocks to delimit the entry phase into this code and then the exit phase. Internally, each of these clearly it represents a critical section code as well, since there is a log operation and then there is a shared resource, the resource counter, that is updated in both of these cases. If we closely examine each of the blocks that we highlighted in the previous example, we will see that they have the form as follows. First, we must log the mutex. Then we have to check on a predicate to determine whether it's okay to actually perform the access. If the predicate is not met, we must wait. The wait itself is associated with the condition variable and a mutex, and this is the exact same mutex that we logged. When we come out of the wait statement, we have to go back to check the predicate, so we have to have the while loop. The wait statement has to be in a while loop. When we ultimately come out of the while loop, because the predicate has been made, we potentially perform some type of update to the shared state. These updates potentially impact something about the predicates that other threads are waiting on. So we should need to notify them by basically notifying the appropriate condition variables. We do that via a signal and a broadcast. And ultimately, we must unlock the mutex. So here, the log construct we said in Burrell's paper, the unlock operation is implicit. In some threading environments, there is an explicit unlock API that we must call. Returning to the readers-writers example, the real critical sections in this case are the read operation and the write operation, right? These are the operations that we want to control, and we want to protect. At the very least, we want to make sure that there isn't a situation where there is concurrently a write operation while others are reading, as well as that there are no concurrent writes. So the code blocks that precede and follow each of these critical sections, both on the reader side that we outlined before and the corresponding ones on the writer side, these we call the enter critical section blocks and the exit critical section blocks. Every single one of these blocks uses the same mutex, counter mutex, and so only one thread at a time will be able to execute within these code blocks. Except that in these code blocks, we only manipulate the resource counter variable. So only one thread at a time can manipulate the resource counter variable. However, potentially multiple threads at a time can be performing concurrently a read file operation. So it looks like these enter critical section blocks are sort of like a log operation that we have to perform before we want to access a resource that we want to protect, that we want to control what kinds of accesses to that shared resource we allow. And then similarly, when we're done with manipulating that shared resource, these exit critical sections are sort of like our unlock. In the plain mutex case, we have to unlock a mutex in order to allow some other thread to proceed. Otherwise, the threads will be blocked indefinitely. Same here. When we finish this critical section, we have to execute this portion of the code in order to allow other threads, writers in this case, to actually go ahead and gain access to the file.